Welcome back to another video in the series about derivatives. Today we're going to talk about differentiability, and this is part one of two videos for differentiability. In part one, we're going to talk about where does a derivative exist and where does it not exist. In part two, which is a different video, we're going to discuss how to find the derivative using a calculator, and so you're going to want to make sure you watch that. So let's talk and review a little bit here about the definition of a derivative. We've said time and time again that a derivative is a rate of change. A derivative is, the definition is the limit of this slope formula between this point that is h away from the point in question. And as h gets smaller and smaller, as h approaches zero, the limit of this slope formula gives us our derivative. And we can find the derivative in one of two ways. We can find it at a specific point, in which case we would evaluate this limit using the point in question. So what value of x are we evaluating the derivative at? And that value would be the slope at that specific spot. It would also be the slope of the line that's tangent there. Now, we can also find an expression for the derivative, which is an equation, and that equation will allow us to evaluate the derivative anywhere along the x-axis. So for any value of x, we can just plug it into the equation and get the derivative. And that is going to be more helpful than doing this limit at a spot. So finding that equation or finding that expression is going to be nice, because then we can plug anything we want into it and get the slope of the tangent anywhere. So let's talk about when a limit does exist. So we've talked about this before in previous videos. A limit exists if and only if the limit approaching the value from the left and a limit approaching the value from the right are approaching the same number. Because remember, the definition of a limit really is what is y trying to become. And if from both directions y is trying to become the same number, well, then the limit will exist. So it only works if from the right and from the left we're approaching the same value. So let's talk about our limit in question. Our limit in question yields the slope, right? So we're talking about the slope. So instead of thinking of this as the limit from the left and the limit from the right, think of it like this. If we have a point in question on our curve, the slope coming from the right and the slope coming from the left have to be approaching the same slope. So if the tangent lines, or rather really what we're exploring here is the secant lines between any 2 points on a curve, if the slopes of those secants are approaching the same slope both from the left and the right, well, then our derivative will exist because this limit will exist. So really, that's what we want to think about. When we have a derivative, essentially it's the derivatives on the left and the derivatives on the right have to be approaching the same derivative. When I say derivative, in your mind, I want you to think slope or rate of change. The slopes from the left and the slopes from the right approach the same slope. The rate of change on the left and the rate of change on the right approach the same rate of change. Those words are all synonymous. They mean the same thing. So when might a derivative not exist? Well, so there are some scenarios that we can think of, right? So the slopes from the left do not equal the slopes from the right. And there's a lot of, this is a very loose interpretation, and I'm sure there's a lot of mathematicians out there that are like cringing that I'm writing this so generically. But when I say the slopes, I'm saying the slopes of the secants, or you can think of them as the slope of the tangent lines, but it's really the slopes of the secants. And remember, the secants connect 2 points. So for example, if I take a look at this parabola here, I want to find the slope right there at that spot on the parabola. What I would do is I would take that spot, and as my secants get closer and closer, whatever these slopes are, so these slopes, the m's from the right, have to be approaching the same value as the m's on the left. So these are, when I say the slope, that's what I mean. It's the slopes of these secants. And if they're approaching the same number, then the derivative exists. So when might it not exist? Well, we've got to think of some scenarios here. And one obvious answer is if you have any sort of discontinuity, right? So let's say we have a piecewise function that kind of looks like this, right? So if you have this scenario, the derivative at that discontinuity is not going to work because the slopes coming from the left are whatever the slope of this line is, and the slopes coming from the right seems to be a horizontal line. So when you have two different slopes, well, it's not going to work. You have a jump discontinuity. So anytime we have sort of a jump or a discontinuity, we're not going to be able to find the derivative there. So let's see if there's any other places that pop up. So the definition of differentiability is this: if the slopes of the tangent lines, and really it's the secant lines, on the left of x equals a, and the slopes of the tangent lines or the secant lines on the right of x equals a are approaching the same slope as x approaches a, well, then we say that the derivatives exist and f of x is differentiable at x equals a. So let's see a couple of scenarios where we might have some issues finding the derivative. So let's consider the absolute value. Now, we've said before that the absolute value of x can be expressed as a piecewise function, where f of x is x for all positive values of x and 0. So it's just itself, right? So the absolute value of 3 is just 3. So f of x is just the x value as long as x is positive or 0. But it's the opposite of x for anything that's negative. So if x is negative 3, the absolute value of negative 3 is the opposite of the x value, positive 3. So here's my absolute value function. It looks like this. So let's consider the slopes of the tangents approaching 0, because at 0 we've got a problem. Because I can find the derivative here. The derivative there is just the slope of the line, which is negative 1. So here, f prime is negative 1. Over here, all along this line, f prime is going to be positive 1, because that's the slope of this curve, or the slope of this line. But here's the problem. They never change because it's linear on either side. And so the behavior of these linear branches of this piecewise function, remember these are linear, and that means you have a constant slope. So you got a slope of 1, you got a slope of negative 1. As soon as we hit 0, remember they have to be approaching the same thing. So when I get to 0, all of a sudden it just flips. There's no value in between, and it's not defined. You can't find the slope at a corner because it's like, well, what is it, 1 or is it negative 1? I don't know. So we have a problem spot right here when we have a corner or a sharp, there we go, sharp corner. So the limit of the slopes coming from the left is negative 1. The limit of the slopes coming from the right is positive 1, so the derivative just doesn't exist there. So we are not differentiable at x equals 0 because, and really it's the limit of the slopes coming from the right and the limit of the slopes coming from the left, because you have a sharp corner. Now that's my visual. So what would I write on my AP exam to make my grader happy? So you would say the f prime of x coming from the right . So backing up, on the AP exam, when you justify your answer, you need to justify it with this definition of the slope. And so instead of using h, we can simplify it just a little bit because it's the idea that the slope on the left and the slope on the right are not the same. So when you justify this answer, really all you need to say is that if 0 is not differentiable, if the derivative doesn't exist at 0 because you see on a graph a sharp corner, here's what you need to write. Don't write that it's a sharp corner, write this. The limit as x approaches 0 from the left of f of x minus f of 0 over x minus 0 does not equal the limit as x approaches 0 from the right of f of x minus f of 0 over x minus 0. So this is the slope formula between any point over here and 0, and then any point on the right and 0. So remember, f of x is your y value. So you're not going to write it using h notation. You're going to just say, as we approach that point in question where I see the sharp curve, the slope between the function and f of 0 and then x and 0 is not going to be the same. And I would write it this time I would write it this way every single time. This is the justification that the AP graders will look for. This is the most succinct way to write it, and this is what's going to give you full credit when you justify that a derivative does not exist. So let's take another look here and just writing it the way the AP exam likes. So consider this function. Here's what the graph looks like. You've got x to the 2/3 power. And let's just review real quick. What this means is that you're taking the cube root of x squared, or the cube root of x and then squaring it. Remember, it doesn't matter the order in which you do the exponent, but that's a fraction exponent. We call it a rational exponent, and that's what it means. So where does the derivative not exist? Well, I see a sharp corner there, but it's not called a corner when we have two curves that come together that way. Here, this is called a cusp. And when we have a cusp, what we do is we say, we see what's happening. And remember, in order for this to be differentiable here at 0, you need the slopes from the left and the slopes from the right of the tangents or the secants to be approaching the same thing. And really, it's the secants. So if we think about what's happening here, the slope on the left, or sorry, the slope on the right between 0 and any f of x point seems to actually be approaching infinity. Because what they're doing is they're getting steeper and steeper and steeper, and they're approaching an infinity. On the left, they're doing the same thing, but on the left, they're negative slopes approaching that infinity. And so what we have is they're approaching some undefined value. Remember, think of infinity. When we think of limits, infinity is an undefined value. It's a concept. So we're getting to become this vertical tangent. And you guys, if the slope is approaching a vertical line, well, that line has an undefined slope. Therefore, the derivative must also be undefined. And so we say that at x equals 0, f of x is not differentiable. Now, in my mind, I'm going to see that there's a cusp, but on my paper, here's what I'm going to write. Because the limit as x approaches 0 from the right, and then I'm just going to do the slope between f of x and whatever the point is, right? F of 0 over x minus 0 does not equal the limit as x approaches 0 from the left of f of x minus f of 0. All over x minus 0. That's the justification that I would write on my paper to get full credit on my AP exam. Remember, you have to not only demonstrate your knowledge on the AP exam, but you have to demonstrate your understanding as it applies to mathematical notation. Now, there are more than one way to write there's more than one way to write this out and get full credit, but again, this is the most succinct way, and if you can get used to writing this as your justification, then you're going to be just fine on a question like this on your AP exam. Now, question 3, can you think of another scenario where the derivative might not exist? Well, take a look here. Here's this piecewise function that we saw earlier. And so let's kind of identify what's happening here. We've got a couple spots where we can't take the derivative, where the derivative doesn't exist, where the function is not differentiable. And so one of these places is right here at x equals 1, and there's another one right here at x equals 2. So at x equals 1, what we have here is we've got this curve that's going to have these slopes approaching whatever it would be there, but then it jumps up and we have this jump discontinuity, and all of a sudden the slope here is 0. So the slopes coming from the left and the slopes coming from the right don't agree. So again, we're going to say the limit as x approaches 1 from the right, and then we're just going to say f of x minus f of 1, x minus 1, does not equal the limit as x approaches 1 from the left of f of x minus f of 1. So the slopes on the left don't equal the slopes on the right, right? So that's the whole point. That's what you need to do. And then the same thing here at 2, because we have this jump, we're going from slopes of 0 on the left-hand side of 2 to whatever the slope is of that linear piece on the right side of 2. Whatever they are, we don't need to say what they are. That's the beautiful thing. This is conceptual. It's saying, I get it. I recognize that the slopes on the left and the slopes on the right don't agree. So we're going to say at x equals 2, the limit as x approaches 2 from the right of f of x minus f of 2 all over 2x minus 2 does not equal the limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2. So the slopes on the right and the slopes on the left are not the same. So therefore, f of x is not differentiable at x equals 1 and x equals 2. Now, there might be other spots along the way, but what we see here, this is what we're going to go based on. And this is a discontinuity. This is a discontinuity. So anytime we have a discontinuity, a sharp corner, or a cusp, remember a cusp is a corner where we have curves instead of straight linear functions. So far, that's what we've got, discontinuity, corners, and cusps. Let's see if we can see one more example where we would have a problem, and that's a vertical tangent. And so let's take a look at a function having a vertical tangent and see what we're talking about. And I kind of discussed it a little bit with that cusp concept, because remember, my lines were approaching infinity. Infinity is an undefined value. The slope being a vertical line, remember, if the derivative is the slope of a line and your line is undefined or has an undefined slope, well, then the derivative is undefined. So if your slope is undefined, your derivative is undefined. That should be pretty obvious. So we can see here we've got a vertical tangent here. And when we try to find the derivative there, and we're going to see this later on, we're going to learn some rules and we're going to learn how to find the derivative of this function without using that limit notation, without using the definition. There's a much quicker way, and maybe you've already figured it out. If you have, that's amazing. But it's actually in one of the next videos coming up very soon. But let's take a look at what happens here. We've got a vertical tangent at 0. You can see that if you consider what's happening with these tangents, well, they're getting steeper and steeper and steeper, and eventually they hit vertical here at 0, and then they go back to not being vertical. So when we look at what the derivative would look like, here it is, it's this purple curve. You can see there's an asymptote there because, hey, the derivatives on the left are approaching infinity. The derivatives on the right are approaching infinity. Ha, that's crazy. It's undefined. And so again, we would write this the same way we've been writing all the other ones. We'd say not differentiable at x equals 0 because the limit as x approaches 0 from the right of the slope between f of x and f of 0 does not equal the limit as x approaches 0 from the left. So even though it's approaching infinity, yeah, they're both approaching infinity, that's great. But remember, not all infinities are equal, so you can't say infinity equals infinity. It's a concept, and some infinities are just bigger than others, and kind of mind-blowing to think about. But anyway, here's your quick recap. A function is differentiable at a point if the slopes of the tangent lines, and I really ought to change that, it's really secant lines. The slopes of the secant lines as x approaches that point from either side approach the same value. A function is differentiable everywhere if at every point on its domain it's differentiable. So you can still have a vertical asymptote. Remember, vertical asymptotes are not considered part of the domain. So if you have a function that has a vertical asymptote, you can still be differentiable everywhere in the domain. So if a function does have a vertical asymptote, it's still differentiable. And then my advice to you, so again, on the graph, you're looking for corners, cusps, discontinuities like jumps and things like that. And then you also want to consider anytime you have a vertical tangent. That's going to be the one that's going to be hidden from you. That's going to be the harder one to figure out. So think about that. Do you have a vertical tangent where the derivative is undefined? But here's my pro tip. I've got actually another one here before we get to this one. So remember, you always want to write that the limit as x approaches a from the right. So a is the point in question. So if x equals a is not differentiable, state this. The limit as x approaches a from the right of f of x minus f of a over x minus a does not equal the limit as x approaches a from the left of f of x minus f of a over x minus a. You have to state it this way to justify your answer on the AP exam. So make sure you make a note of that. And then here's my other AP exam pro tip. If you are told that a function is differentiable, what other hidden information are you told? Now we talked about if it's not differentiable at corners, cusps, But then there was one other piece in there, and that was discontinuity. So if you're told that a function is differentiable, you're also told that it is continuous. So differentiable implies continuity, but continuity does not imply differentiability. It's a one-way street. If you're differentiable, you must be continuous. But just because you're continuous, like the absolute value function, doesn't mean you're going to be differentiable everywhere. So I hope that this was a helpful video for you, and I hope you're taking note of all the AP exam, how to write your answer to get full credit help that's in there. And you know, this comes from going through and reading past questions and seeing how do they want you to state your answer, and what students get full credit and what students don't. And all of that is available at the AP, at the College Board AP website, and they're all public, and you can go through and you can start reading through AP exam questions to really prepare yourself for what is the caliber of questions that I'm going to be faced with on my exam, and how am I going to state my answer. And they provide student examples for each question. Each one has 3 examples, one with a perfect score, one with a score in the middle, and one with a low score. So you can really see what are the mistakes that students have made in the past, and why aren't they getting full credit, and how can I do my best to get an exam score worthy of the knowledge and the work that I am putting in. So I am here for you, and you can do this. And yeah, my encouragement as always to you is to keep on going, because you know what? You really do have this.